the study of a high-mobility heavy-duty hexapod robot for challenging field terrains, design, modeling, and experimental validation. In this study, we present Elspider-IV, a heavy-duty hexapod robot developed using a generalizable and systematic design methodology. The design framework begins with the overall design and analysis of the robot's mobility system. Based on terrain-specific performance metrics such as slope angle, obstacle height, and ravine width, we determine the structural layout and body dimensions. The leg mechanism is designed to meet kinematic constraints, and its reachable workspace is analyzed accordingly. We then conduct terrain traversability analysis, modeling the robot's interaction with 5 representative terrain types: slope, lateral slope, ravine, obstacle, and composite obstacles. Using static stability margin analysis, we derive analytical constraints that link terrain features to the robot's geometric parameters, ensuring stability and mobility. To validate the design, we build a simulation platform to emulate diverse terrain conditions. Time series analysis of joint displacement, velocity, and force under each scenario provides the envelope of actuator demand. These results are used to select appropriate actuators and confirm system feasibility before prototype fabrication. To validate the robot's terrain adaptability and structural design, we conducted extensive simulation experiments based on the Vortex Dynamics engine. 6 representative terrain scenarios were modeled, including flat terrain, slope, lateral slope, ravine, obstacle. In each case, the robot executes per planned gates while navigating complex features. During locomotion, joint performance is continuously monitored. Time series curves of joint displacement, velocity, and contact force are dynamically overlaid in real time, as shown in the embedded visualization windows. These dynamic plots reveal that the joint trajectories remain smooth across all terrains, and actuator responses stay within the design limits, confirming the adequacy of our envelope-based actuator selection method. The simulation results not only demonstrate stable movement under varied conditions, but also serve as a critical link between analytical modeling and physical prototype validation. To verify whether the physical prototype meets the design metrics, corresponding experimental scenarios are constructed for validation. Essential data related to the robot's body during walking are measured, and data from the leg joints are also collected to comprehensively evaluate the robot's locomotion performance. In Experiment 1, we demonstrate the fast walking capability of the Elspider-IV hexapod robot on flat terrain. The robot is commanded to perform a symmetric tripod gait with a target forward velocity of 5 km/h, thanks to its modular leg design and optimized actuator configuration. The robot maintains stable locomotion without excessive vibration or foot slippage. In Experiment 2, we validate the heavy load walking capability of the Elspider-IV. The robot is loaded with payloads weighing approximately 1.3 tons, reaching the system's rated maximum load capacity. A waving gait is employed to maximize support stability, ensuring at least 5 legs remain in contact with the ground throughout the motion cycle. Despite the substantial load, the robot maintains good ground contact, stable body posture, and balanced leg coordination. No excessive joint torque or foot slippage is observed during the test, confirming the reliability of the actuator design and structural strength. This experiment demonstrates the robot's ability to transport heavy payloads, which is essential for logistics, construction, and disaster response missions in unstructured environments. In Experiment 3, we demonstrate the slope climbing capability of the hexapod robot under extreme terrain inclination. The test is conducted on a rigid slope surface inclined at 35 degrees, which is near the upper limit of the robot's terrain adaptability. A diagonal gait is employed, allowing alternating pairs of legs to move while the other 4 legs maintain support, ensuring dynamic balance and traction. As the robot ascends the slope, its posture remains stable, with the body kept approximately parallel to the terrain plane. The robot exhibits steady foot placement, minimal body pitch oscillation, and no signs of serious slipping or instability. This test validates the robot's ability to climb steep inclines while maintaining quasi-static stability. In Experiment 4, we demonstrate the hexapod robot traversing a 20-degree lateral slope, which challenges both the robot's anti-overturning stability and terrain adaptability. During lateral walking, the robot employs a diagonal gait, ensuring that at least 4 legs are in contact with the ground at all times. Providing a wide support polygon, the body maintains a horizontal posture throughout the traversal, enabled by real-time feedback control of the center of mass. To further evaluate the walking stability and comfort, we compared the whole body vibration levels of the hexapod robot. The robot successfully completes the traversal without sliding or tilting, demonstrating its robust static stability and torque margin under lateral loading conditions. This test confirms the robot's ability to handle cross-slope locomotion, which is essential for off-road scenarios such as hillside inspection, forest patrol, or rescue tasks. In Experiment 5, Elspider-IV performs a ravine crossing maneuver on a 1-meter wide ravine using a predefined gate strategy. The robot first approaches the ravine and shifts its center of mass to ensure the front legs have enough workspace. It then uses its front and middle legs to establish a stable support polygon across the ravine. As the hind legs lift off and swing forward, the system continuously adjusts and maintains stability. The test demonstrates the robot's ability to maintain static stability throughout the process, with the center of mass projection always within the support triangle. The stepping length and reach of the legs are verified to meet the terrain requirements, validating the robot's structural and workspace design. Overall, Elspider-IV successfully traverses the ravine while maintaining full body stability and without foot slippage, showing strong terrain adaptability. In Experiment 6, Elspider-IV is tasked with climbing a 1-meter high convex obstacle using a pre-planned walking gait. The robot approaches the obstacle and raises its front legs while adjusting its pitch angle to maintain balance. Once the front legs establish contact with the upper platform, the robot gradually shifts its center of mass forward and elevates the middle legs. During the ascent, real-time sensing and pre-tuned foot trajectories ensure sufficient clearance, avoiding collisions with the obstacle edge. After all legs cross the convex obstacle, the robot establishes full body support and proceeds to walk stably. The successful completion of this trial confirms Elspider-IV's high obstacle climbing ability, large stepping range, and reliable stability during complex motion transitions. In this comprehensive field experiment, Elspider-IV is deployed across a variety of natural terrains to evaluate its terrain adaptability and locomotion robustness. On asphalt pavement, the robot walks at high speed with minimal vibration, demonstrating smooth control and efficient locomotion. On soft soil, Elspider-IV maintains stable movement despite uneven ground reaction forces. The shock-absorbing foot design reduces impact. On snow-covered surfaces, the robot successfully completes walking tasks using low-speed gaits, adapting to low-friction terrain without losing balance. When walking on both longitudinal and lateral grassy slopes, Elspider-IV dynamically adjusts its body posture to maintain stable. Finally, in complex composite terrain that includes steps, slopes, and uneven transitions, Elspider-IV maintains steady progress by autonomously coordinating its legs and adjusting foot trajectories. The results confirm that Elspider-IV is capable of operating reliably and safely across diverse outdoor terrains, validating the design's practical robustness and general applicability. We compared the performance metrics with typical heavy-duty legged robots, including walking velocity and load-bearing capacity. Elspider-IV has a maximum walking velocity of 5 km per hour and a load-bearing capacity over 1 ton. And Table 11 presents a comparison between Elspider-IV and several existing heavy-duty legged robots. It can be seen that Elspider-IV demonstrates excellent mobility and load-bearing capabilities. Although some legged robots exhibit higher walking velocities than Elspider-IV, the latter possesses superior terrain adaptability. In addition, Elspider-IV is capable of climbing various obstacles in complex terrains, ensuring high terrain traversability. For more information, please contact us with our emails.